All right. Good evening, everyone.
Good
Uh,
evening.
Hi there.
so, all right, I'm Rich Ozer, and we're here at the Chabot Space and Science Center at the 36-inch research telescope that we fondly know as Nellie. And I'm here with Gerald McKeegan and John Curry. And we're cutting it close tonight. It's we got a humidity right now of what is it at, Gerald?
It
81?
is 82 right now.
Oh my. So we're good till it hits 85. Once it hits 85, we have to close the telescope because we don't want water condensing on the mirror, and we can't really operate it once everything hits its dew point because it would all fog up anyway. So why don't we get started right away so at least we could see something. And I'm going to share my screen if I could figure out how to do that. Hold on. Here we go. Bear with me, folks.
So while Richard is doing that, let me tell you a little bit about our telescope. We're up here at the Chabot Space and Science Center, and we're in the observatory with our 36-inch reflecting telescope, the one we call Nellie. Nellie is our newest telescope. It was built in 2003, and it is a 36-inch reflector, so it uses mirrors instead of lenses. And as you can see, it can give some pretty good images of the planets. What you see right now is the planet Mars. And it's a pretty steady image, which suggests that we've got some pretty calm air tonight. Unfortunately, it's also cold and humid air, so we're fighting the humidity. So Mars is the fourth planet from the sun. It's about half again as far from the sun as the Earth. And Richard, I can actually see a little hint of the polar ice cap
Yeah, I
about
do
the 8
too.
o'clock position there.
Yep,
So,
I sure do. I'm
yeah.
gonna, if you don't mind, I'm gonna center it here just to,
Okay. All right.
whoops, wrong way.
Yep.
All right.
Yeah, you went too
Moves kind of
far.
fast, doesn't it?
You went
It
too far.
does. Well, I had to let go of that center button.
Yeah.
There we go. Just want to make sure we're good. Oh,
It's
So,
really slow without that button.
so
yeah.
Mars is a smaller planet than the Earth. Mars is about half the diameter of the Earth. And it has less mass, obviously. So gravitational pull at the surface of Mars is less than it would be on Earth. If you were walking around on Mars, you'd weigh only 38% of what you weigh here on Earth. So if you're looking for a weight loss program, after spending so much time, at home in COVID lockdown, Mars is the place to go.
Didn't we discuss this last week?
Yes, yeah, your mass does not change, but your weight will change.
Yeah.
Yeah, so,
Well, your mass might change because there's not a lot of things to eat on Mars.
Just
well,
potatoes.
Oh
yeah,
yeah, just
yeah,
potatoes.
and the fact that the atmosphere is only 1/100th the density here on Earth means that whatever weight you have in terms of air in your lungs is going to get sucked right out. So it's probably not a good idea. So
Yeah.
Yeah.
So, like I said, the atmosphere on Mars, the density of the atmosphere is 1/100th of the atmospheric density at the surface of Earth. So, if you walked outside on Mars, it would be like walking into a vacuum. It's technically not a vacuum. In fact, Mars has winds and it has occasional clouds. So it does have some weather. It's just very thin air up there. Also, the air is there's hardly any oxygen in the air. It's mostly carbon dioxide. And you'll see if you looked at about the 7 o'clock position, between 7 and 8 o'clock position, down in the lower left of the disk of Mars, especially in the magnified view there, you can see a little white patch, and that white patch is the south polar ice cap of Mars. Um, Mars has polar ice caps, just like the Earth does. although they change a lot more dramatically than the Earth's does, especially the northern polar ice cap. It becomes quite large in northern winter. But the ice in the polar ice caps is primarily carbon dioxide ice. There is water ice as well, but most of the ice that we see on the poles is carbon dioxide ice. There's a water ice elsewhere on Mars, but it's underground. In fact, they've found evidence of underground water, mostly in the form of ice, in numerous locations on Mars. And there's some speculation that there may actually be liquid aquifers down deep in the ground as well. So, that's the good news. When it's time to go to Mars, we'll at least have water to use. Now you see the color of Mars. It's kind of a rusty brown color. We call it the red planet, although as you can see, it's not truly red. Most of the color, the lighter color that you see, is in the northern half of the planet, which has fewer mountains. It's more like desert regions. A long time ago, Mars had volcanoes. And when those volcanoes were spewing dust into the air, a lot of it settled mostly into the northern half of the planet. So it produced these large deserty areas. And if you get up close to them, you'll see that there's a lot fewer craters and not much in the way of mountains and so on in those regions. But in the southern half of the planet, it's much more rocky, more mountainous, and a whole lot more craters in the southern half of the planet. That's older terrain with less volcanic dust. Now, the volcanoes are not active anymore. They've likely not been active for several million years. The volcanoes are still there, but they're just not active anymore. In fact, the largest volcano in the solar system is on Mars. It's called Olympus Mons, and Olympus Mons is 3 times the height of Mount Everest, and the base of Olympus Mons is the size of the state of Arizona. So it's one huge volcano. And let's see, what else can I tell you about Mars? We periodically detect methane in the atmosphere of Mars, and there's a lot of debate about why that is. One of the most common sources of recurring methane in an atmosphere is life. So, it's an indication that there may be some form of life on Mars that periodically produces methane. It's hard to come up with another explanation, a natural process other than life, to account for the fact that we repeatedly detect methane in the atmosphere. If it was just a one-time event, it should dissipate fairly rapidly and then not be detected again. But we keep detecting it multiple times, so it's not proof of life, but it certainly suggests that there might be some form of life on Mars. All right.
Well, the other thing I could say is that the seeing tonight is a lot better than in previous week.
Yeah.
We could actually see some real detail, the surface features there. And that was evading us last week and the week before.
The humidity has actually gone down a little bit. So
hey, we're good.
Keep your fingers crossed here. So
are people, somebody's mentioning that they have lost the broadcast. Is that true? Can I get some thumbs up if you're able to?
I'm still
see
seeing
us?
it.
Yeah, I'm still seeing it too. So I don't think. Yeah, I see people jumping in, and David just commented on the image. So I think we're okay. So Patrick, I don't know what's going on. Yeah, thank you. We get a little paranoid about the streaming.
Yeah.
We're doing something a little different tonight too. We're using a different streaming technology because we're also going out to our YouTube channel, and so we're trying some new stuff. And I'm always paranoid that I made a mistake. All right, where to?
Well, I don't know. Let's see. We can't go to planets anymore because, or we can't go to Jupiter and Saturn anymore. For the past several weeks, we've been looking at Jupiter and Saturn, but each night, the two of them drift a little bit farther to the west and get a little bit closer to the western horizon, and they are now both too low for us to observe with this telescope. They're still in the night sky, but this telescope can't look at anything that's less than 15 degrees above the horizon, and unfortunately, both of them are now less than 15 degrees above the horizon. So if you want to see Jupiter and Saturn, you're going to have to go outside and look in the night sky. So I was thinking we might want to
How about Neptune?
Neptune, sure.
All right. Neptune's a planet. It hasn't been demoted yet.
Well, stay tuned.
Yeah. All right.
Yeah. Okay. Here we go. Let me synchronize this.
If I recall, I can't get Neptune on live view. I have to do exposures.
Yeah,
It's pretty dim.
Yeah.
Yep.
Yeah.
So
And it won't be very
prepared to do that.
big. You know, we see Mars as a nice disk with features on it. Unfortunately, when we go to Neptune, that's not going to be the case. Neptune is going to look like just barely perceptible as a disk, and it'll have a bluish color to it, but it'll be cool to be able to see it. So we are there, Richard. So if you want to start your exposure.
Yep. Let me.
So with dimmer objects like this, we can't use a live view with our camera. So what we have to do is use long exposures. And so I'm assuming you're going to do something like 25-second exposure. Okay.
Yep.
And so we'll wait till that exposure comes through and we'll see if we can see Neptune. Neptune is the 8th full-size planet from the sun. It's 30 times farther from the sun than the Earth. So it's way out there. It's very cold out there. Neptune has a large moon called Triton that has a atmosphere, mostly nitrogen, and there's nitrogen ice on the planet. Aha, I see it.
There it is. And we also see next to it
Triton.
Triton.
Yeah.
Its moon.
Yep.
Nice exposure there.
Yeah. Yeah. I repositioned the telescope a little bit. So you can see that bright, much larger dot than the stars around it. That's Neptune. And then you see a little tiny dot right next to it, and that's its moon, Triton. Now, it doesn't show up very well in this image here. If you were looking with your naked eye, Neptune would have a very distinct bluish color to it. So probably we're a little overexposed here, but that's okay.
Yeah. I wanted to get it positioned right, and then we'll try a slightly shorter exposure and see how that looks.
Okay. Did it move?
Give it a sec. Yeah, that's fine. That's fine.
Yeah.
And there we go. So you can see Triton real well there.
Yeah.
But you're right, it is a bit overexposed. All right, let's go.
Of course, if we get Triton or Neptune exposed right, we're probably not going to be able to see Triton, right?
So, yeah, that's probably true.
So one of the cool things about Triton is it has these cryogenic volcanoes. They're not lava like what we have here on Earth or some of the other planets. These are nitrogen volcanoes and water ice that's on Triton. And it does have like I say, a nitrogen atmosphere. There we go. Got it all centered up real nicely.
Yeah, there we go.
And of course, Neptune is a gas giant. Well, we get a hint of the blue there. It's a gas giant. It's a little over 4 times the diameter of the Earth. And like I say, it's way out there. And like the other gas giants, when we take close-up images, such as those taken by the Voyager spacecraft, we see that because of its rapid rotation, it's got bands around it, just different shades of blue. And it even has a couple of cyclonic features similar to the Great Red Spot. But it is way far away, so even though it's big, it's so far away, we can't see much more than what you see here. This is pretty typical of what we see when we look at it with our telescope.
Now, sometimes it'd be with the nature of the orbits of Neptune and Pluto. Doesn't the orbit of Pluto sometimes go inside the orbit of Neptune?
It
So
goes,
so sometimes Neptune is the ninth planet. If you count Pluto as a planet, which Gerald does.
let's not go.
Oh, this is going to open up a
All
whole
right.
can of worms here.
All right, fake
Here we
news.
go.
Forget it.
Yeah,
I don't want to get the IAU on our back.
yeah, or Neil deGrasse Tyson. You know?
They'll shut us down. The IAU police will come.
Yeah.
There are other dwarf planets that do that as well. Is that not true, Gerald?
Do what?
Come closer to the sun than Neptune.
There's actually several planets out in the same region as Pluto,
Yeah.
and they are in elongated elliptical orbits. And
there's a name for
more-
that, but it eludes me at the moment. It's a strange long syllable name for planets that move closer than Neptune.
Oh, yeah, I don't remember off the top of my head. One of the interesting things about Pluto and the other planets that are roughly the same distance from the sun as Pluto is that they are in what we call the 3-2 mean motion resonance with Neptune. So for every 3 orbits around the sun that Neptune makes, Pluto makes 2 orbits around the sun. So we say that they are in resonance with each other, and that particular region is where the 3-2 resonance is. So all of the objects that are similar distance to Pluto have that same feature. They orbit twice for every 3 orbits of Neptune.
Stephen would like to know what the temperature is on Neptune. Do we have that handy, or should I look it up?
Probably have to look it up.
All right, I'll do that.
I guarantee you it'll be cold, whatever number it is.
Yes, it'll be colder than here.
So I have an image I'd like to share, Richard, if I can.
Yeah, let me allow that. Hold on for a sec here.
So I have a Voyager image of Neptune close up.
Sorry, I've got to. Sorry, Gerald, it's not letting me get to that screen yet. Having some technical issues here.
Yeah, okay. Well, we'll just wing it on. There's a question that came up on YouTube, whether or not we're going to be able to see Andromeda tonight. As it turns out, Andromeda is really very large on the sky. It is actually its size. If you could turn up the brightness so you could see it easily with your naked eye.
You could do it now. Sorry.
It's 4 times the diameter of the full moon. So Andromeda is very big. Our field of view with this telescope and this camera setting is less than half the diameter of the full moon. So if we tried to look at Andromeda with this telescope, you'd see a big fuzzy blob that takes up most of the frame, and it's only a small portion of the total galaxy. So we tend not to do that when we're okay.
We had a question on while you're getting your video. Oh, you can't share yet?
Yeah, it says you cannot start screen share while the other participant is sharing.
Let me stop sharing here.
Okay.
All right. Now you can do it.
All right.
We had a question on our YouTube feed. which is can we look at Andromeda? And because
Yeah,
of the
that's, I
focal
just
length
answered.
of
I just answered
yeah.
that question.
Oh, got it. Well, what I wasn't listening because I was busy with our technical
Oh,
issues.
yeah,
So
I just
great.
answered
There
it.
you go. There you go.
Okay.
But what I do want to say is we are going to look at another galaxy, hopefully in the Andromeda in the Andromeda constellation. So
Yeah,
I won't repeat what you just said.
So here's a close-up of Neptune. This was taken by
Nice.
Voyager spacecraft, and you can see it's got a lot of banding like Jupiter and Saturn have, but it's also got some cyclonic activity, and this it changes over time. So we've seen that these cyclones come and go, just like a lot of the ones on Jupiter do. So. John, have you figured out how cold it is up there yet?
Yeah, minus 392 Fahrenheit.
Oh, balmy day.
Yes.
Oh, look at that. I'm grainy again.
Germ says the coldest winter he's ever experienced was the summer on Neptune.
Yeah, right.
I've heard something like that before.
Yeah.
Oh, you're grainy again. There you go.
Yeah, I tell you.
I don't know.
Get me off of there.
It happens every time you talk about Andromeda.
I guess, yeah. Okay, so we are going to do what? Go to a galaxy here?
Yeah, why don't we look at NGC? You might need an intermediate star.
Where is
it?
it?
But it's NGC 891 in Andromeda, I believe.
Oh, okay.
It's either Andromeda or Triangulum, but I think it's Andromeda.
Okay, I'm going to go back to Alpha Rats and we'll sync on that.
Yeah, I'd say that was a good idea.
All right, so the telescope that we're using is computer controlled. It is our only computer controlled here. We have two much older telescopes that are manual telescopes, but this one is computer controlled. So when we want to go to an object, we just go to the computer screen, tell it where we want to go, and the computer does all the work for us. So I want to go to live view there.
I have to get this thing canceled here. Hold on for a moment. My Zoom console was blocking the abort button. Too many pieces of software running all at once.
Yeah, really.
And they all want control.
They all want control. That's exactly right. Here we go. Let's get it bullseyed.
Okay, and so we got to go north here a little bit, and then we got to go west a little bit. So even though the telescope is computer controlled, it's not absolutely perfect. So as we move around the sky, sometimes the telescope is a little off from where we think it's pointed. So we do this process we call synchronizing, where we pick a bright object like a bright star, we synchronize on it, and then we move to the object that we want to move to. And so, okay, Richard, it was NGC what?
891.
NGC 891. All right. Likes it, and here we go.
We got some questions in the meantime, wanting us to talk about cryogenic volcanoes.
Oh,
well, they call them cryogenic because instead of spewing lava, they spew ice.
Mm-hmm.
And we actually see that on a number of places, like Europa, the moon of Jupiter, and Enceladus, moon of Mars, or Saturn rather. Boy.
It's the cold weather.
Yeah. So I see something in the frame there.
Yeah, that was the bright star you were just on before. I'm photographing
the
galaxy right now. So hopefully we are.
So what can you tell us about this galaxy, Richard? Looks like
it is a edge-on spiral galaxy, and I am going to have to look up the distance.
NGC?
There we go. Hold on, 891, and I'm going to have to bump up the contrast here. You're able to just kind of barely see it here, but I know we can get a better view of this. Okay, I'm gonna change some of the settings here. Let me abort this. Take it off.
Oh, Starry Night doesn't have a distance on it. Let's see.
Yeah, I've got a distance of 27.3 plus or minus 1.8
Yeah,
million light years.
in the description it said 30 million, so that's pretty close. Okay.
Yeah.
Okay, I'm gonna bump up the time and the ISO to try to bring this out a little bit better, because you're probably not seeing much at home here. You're seeing maybe a little brownish. I kind of see it on my Facebook screen on my phone.
Almost vertical, slightly tipped to the left.
It's a very thin spiral.
Oh, by the way, we're down to
edge.
79%, so we're doing good.
We're good. Yeah, we're good for the night. Probably. It keeps dropping.
Don't say things like that.
I'm knocking on wood. I'm throwing salt over my shoulder.
Sure.
There's no black cats in here. They're all in my house. Let's see how this one comes out.
So this is how it is with these really faint objects. They're out there.
There we go.
And we can see them, but we can't just view them the way you would, a bright planet or something like that. We have to use long exposure photography. To get a really, really good image of this object, we'd have to do multiple exposures over a long period of time, and then take all those individual images, sort through and pick out the best ones, and then stack those electronically. And that's how you produce really nice, high contrast, high resolution images of galaxies out there in space. The live view method doesn't work very well.
Yeah, well, it actually doesn't work at all for something this dim. This is like an 10 or 11th magnitude galaxy.
So one of the nice things you can see, since this is an edge-on galaxy, you can see the central bulge. That's that light patch in the center, and you see it's divided in half by a dark line. And that's a dust lane in the spiral arms of the galaxy. A lot of the spiral galaxies have fairly dense dust lanes in them, and the dust clouds are where new stars are forming, and gas and dust forms these huge clouds. You can actually see one in the Milky Way if you find a dark location here on Earth, and wait till the middle of the summertime. You can actually see a elongated dark gas and dust cloud that obscures part of the Milky Way, and we see it in many other galaxies as well. So you see that dark band right through the middle of the galaxy. There you go. There you go.
All right, so I have to really push it here. So you'll notice all the additional noise that's in this picture, but it does bring out the galaxy, and now you can see that dust lane that Gerald is talking about. The additional noise is because I bumped up the ISO, which is the sensitivity of the sensor, all the way to 6400, which I think is as high as, no, it doesn't go, it goes higher on this camera, but it'll be really noisy if I go to 12,000. But this gives you a good idea of what it looks like.
Now, one of the things about those big, huge gas and dust clouds is that that is where new stars form. If we were to look at a spiral galaxy in infrared instead of visible light, we would see that all of the new star formation is going on in the dust lanes rather than just the spiral arms. And that's because stars form by condensing clouds of gas and dust. So put on your infrared goggles, and you might be able to see a few forming stars in this dust lane. Nobody has infrared goggles, huh?
No, I don't have them today.
I tried.
Yeah, well, but it's actually it's a funny statement, but it's not that far from the truth. When photographing a galaxy like this, if you want to see those star forming regions, you use what's called a hydrogen alpha filter. And that's a particular filter you can put in front of your camera. And with a long exposure, you're able to make the whole system most sensitive to those star forming regions, bring them out, and then assign them a unique color in your photograph so you can display them along with the red, green, and blue of the galaxy. All right.
Well, that's actually a pretty good image. So
Yeah, it's not bad
I
at
think
all.
so. Yeah.
For a single shot. Yeah. If you want to, there's something I wouldn't mind trying, but we could maybe, if you want to do something else first. The challenge object I was wanting to do, I've been wanting to do this for a while, is NGC 404, which is the ghost of Mirak, which is a lenticular galaxy, which is kind of a halfway between a spiral galaxy and an elliptical galaxy, just next to Mirak. It's called Mirak's Ghost.
Okay.
And
well, I could find Mirak, but
yeah, that's pretty much all you got to do is find Mirak or search for NGC 404. It's just off of Mirak.
Okay. Well, I'll tell you what.
And I don't know if we can capture this or not because Mirak is so bright, and I just don't know if this system will be able to make the distinction between the two.
Yeah, it's really in the brightness of.
Yeah,
Mirak.
it is.
Yeah.
I usually use it to judge seeing, and tonight is a good seeing night, so we might be able to.
Okay, I'm slowing to
apart.
Mirak.
All right.
That should be
First
bright.
I'll go to frame and focus and make sure we're there. Because at least Mirak, yeah, we're close. So let's get it centered.
Okay.
Now Mirak's is Mirak a red giant star? Or is it's kind of reddish.
Yeah, it's reddish, so it probably is a red giant. Yeah.
All right.
For it to
and
be
now,
that bright.
It's also a double star.
Oh, I didn't know that. All right, so I'm going to actually bring the ISO a little bit down.
So you think it's going to be in the same field of view?
Yeah, it should be just next to it. So let's try that. Again, it's a little bit different with Nellie. Nellie's got such a long focal length. I may be underestimating the distance between the two. This may be a fool's errand.
Yeah. So we've got a couple of other easier to see objects that we'll look at tonight. We'll look at a globular star cluster, and maybe we'll look at another planetary nebula or two, and bounce around, see what else we can see.
Mirak is a cool red Class M giant, according to Starry Night.
Okay, let's see what this does now. Whoa, that's nice and bright, but I don't see it.
I don't see.
Yeah, there's Mirak.
Oh, wow.
That's pretty cool in and of itself. I don't see a galaxy there at all, and it may be that it's farther off. Does your image of the sky indicate where on the star field it might be? Because we have a pretty good sense of the star field here.
I'm gonna have to zoom way in for us to see anything like that.
I don't want to spend too much time on this, but it would be fun if we could see it.
Yeah, this doesn't even show it. What's the NGC number?
404.
Well, let's see what happens when I do this.
Actually, there are two bright objects right at the edge of the sparkly area.
Well, there's
one of those may actually be
the double?
The galaxy.
Oh, the galaxy.
Okay, it may actually be outside of our field of view.
That's what I'm thinking.
So I'm going to go ahead and slew where the software says it is. Here we go. It's not much of a slew.
Yeah, it's probably enough.
Okay. So try it now.
All right, here we go. That's quite a pattern that the camera produced with the star. I kind of like that. Look, we caught a star in mid-explosion.
You see that?
Don't say that. You get everybody excited here.
No, I know it's not true. No, the reason it looks that way is we're basically filling up the wells in each of the pixels on the camera.
Yeah,
It's so
yeah.
bright, and it spills over to adjacent pixels and makes that big starburst pattern.
You see the object right at the edge of the star at 9 o'clock?
Yeah.
According to Starry Night, that is about where the galaxy is.
Oh,
maybe
no,
not.
Oh, here it is.
No,
This is it.
Yeah, there
That's
it is.
the galaxy. So let's see if I could enhance that at all. That's a little too bright there. It's very touchy here. So you could see the core of the galaxy and kind of the brightish area. It's elongated in, I believe, this direction.
Yeah.
Yes.
Yeah.
So this is called a lenticular galaxy, and a lenticular galaxy is it has spiral arms like a spiral galaxy, but they're much less defined. They've kind of become cloudy, they've lost their contrast, and there's not a lot of new star formation going on. And then these lenticular galaxies eventually evolve into, at least the theory goes, into elliptical galaxies, which are basically elongated white blobs that are very common in the sky. They're as common as spiral galaxies, but that's the way galaxies age: spiral, lenticular, and then elliptical. But yeah, it's pretty neat. We can see that.
Yeah, and you can see the glare from
Mirak right here,
right down
Yep.
there in the corner. So
All right. Well, I'm happy.
yeah. So we're pretty close to M33. You want to give that a shot?
Yeah, absolutely.
Oh, why not?
Maybe we'll get lucky. This is called the Pinwheel Galaxy.
M33 is one of my favorite galaxies to look at, so it's a challenging object though for its own reasons. All right, I'm gonna
And
go
since we had
this.
questions about Andromeda earlier, it is right next to Andromeda.
Well, not exactly right.
Not in distance, but
Yeah.
in the position in the sky.
Yeah, in apparent position. That's
Okay.
right. I said that the other day. What did I say? Or one of us said that Saturn was right next to Jupiter.
Yeah.
And then we had to.
Good way to get a lot of questions.
We had to shift it to three-dimensional thinking.
Yeah.
So when you say right next to it, John, it's actually on the opposite side of Mirak from M31. So I'm not sure how right next to it you meant. There's M32.
Maybe I'm thinking of
there's
wrong
M32.
galaxy. Yeah,
the M32 is right next to M31.
Yeah, I'm thinking of M32. I'm sorry.
And M110 is also.
Disregard everything I've said.
Okay.
Oh, nice. Here we go. Okay. So let me improve the contrast here if I can. I'll probably take an exposure at a higher ISO too, but see what we could do with this. No, all right. I'm going to take a longer. I'm going to take a more sensitive exposure in a sec here.
So this is another spiral galaxy, and
we'll go to 64.
It's kind of at an angle such that we can actually see the spiral arms in it.
The next image will bring that out a little bit better. Now, M33 is it's got a magnitude of, I believe,
6.5.
Oh, really? 6.5?
But
that's the overall magnitude across the surface. The actual surface brightness is much lower than that. So there are other magnitude 6 objects where the light is more concentrated into a smaller space, and they're easier to see. M33 is always a little more of a challenge.
Yeah, M33 is also smaller than M31, the Andromeda Galaxy. In fact, it's smaller than the Milky Way galaxy.
Okay.
Its distance is only a little farther than the Andromeda Galaxy, but as you can see, we can get most of it in our field of view. Whereas with the Andromeda, we wouldn't be able to get only a small fraction of it in our field of view. So we think M33 is about 2.7 million light years away.
There we go.
And it's about 60,000 light years across, whereas the Milky Way is a little over 100,000, and Andromeda is even bigger than the Milky Way. So sometimes this is called the Pinwheel Galaxy. Sometimes it's called the Triangulum Galaxy. It's in the constellation Triangulum.
What I'd like to point out on this, though, is some of these star-forming regions that make this a very interesting galaxy to look at and photograph with much longer exposures. I mean, I know people who've put in hundreds of hours of photographing this galaxy and have incredible amounts of detail. But right here is one of the notable star-forming regions in the galaxy. So we're not just looking at this core area. This galaxy extends out all the way through this field. Here's another star-forming region. Here's another star-forming region. And basically, these little knots of stars that you see speckled around M33 are all areas where new stars are emerging, where there's high density hydrogen gas in these clouds, and these regions come out quite well with a hydrogen alpha filter, which is what I was talking about a little bit earlier.
It's worth noting also that all of the stars that you see in that image are all part of the Milky Way galaxy. They're not.
Yeah, these individual stars,
galaxy.
like this chain of stars here, which is, I think, really neat looking, is actually part of the Milky Way. These this bright star here is Milky Way. That's Milky Way. This is the core of M33, so that's not Milky Way. That's a Milky Way star. But these knots that I've been pointing at, like here and here and here, those are all part of M33.
Cool. Somebody asked if it's the same age as the Milky Way. It's probably roughly the same age. So the Milky Way, we think, is somewhere around 11 or 12 billion years old, and it's likely that M33 is similar in age. M33, the Milky Way, M31, and a few other galaxies are all part of what we call the local cluster. It's a cluster of galaxies that all seem to kind of hang together and are likely all similar in age.
You almost said the local custard. Yeah. and now I'm hungry.
Yeah, that must tell you that I haven't had anything to eat for a while.
No, I guess. Yeah, I had a late lunch. I haven't had dinner.
I have a question from Tim on YouTube. What about the Horsehead Nebula or a similar nebula? Horsehead is not something we could easily photograph quickly on this, and it's way too low at the moment.
The Horsehead
is just barely coming up now.
Yeah, we'll be looking at Orion, obviously the famous Orion Nebula, and maybe some of the other nebula that are associated with the constellation Orion a little bit later in the season. We'll save that for December, January, when it comes up a little bit more at 9 o'clock. The Horsehead is a difficult object to photograph well. It requires not only narrowband filters to get a good image of it, but it requires a really dark sky. It's you can do narrowband imaging in the city and pick up the Horsehead, but we would need lengthy guided exposures to do it. So I would not expect that we're going to be able to see that even through our telescope. Not to say we won't necessarily give it a try, but it's not gonna.
We'll try anything once.
We'll try anything once. Yeah.
So, if he wants a nebula, we have a nebula that we can look at that's not too far away, the blue Snowball.
Yeah, let's look at the blue Snowball. That way
All
we
right.
can get a planetary nebula in here.
All right. So
different kind of nebula, but nebula still.
Yep. So the blue Snowball is what we call a planetary nebula. There are actually many of them out there. And planetary nebulae are the remnant of dying stars. So stars like our sun, and even stars more massive than our sun, a little bit more massive than our sun, or less massive than our sun. And they, when they die, they swell up and become red giants. And as a red giant, they're generating a lot of internal winds, and the gravitational hold on the outer layers, because they're now so big, their gravitational hold on their outer layers is not real strong. So those internal winds start blowing gas off the outer layers of the star. And that goes on for several tens of thousands of years, maybe 100,000 years or so. And it strips away quite a bit of the mass of the star, exposing the inner part of the star down near where the core is, where it's a lot hotter. Eventually, the fusion process at the center of the star, or in its core, dies out and stops. And the pressure that results from that fusion stops, and then whatever's left of the star collapses and becomes what's called a white dwarf. And a white dwarf is all the remaining mass of the star compressed down into a very small object, maybe the diameter of the Earth. And it's extremely hot. It's so hot that it emits a lot of its energy as ultraviolet radiation. And that white dwarf is surrounded by this cloud of gas and dust that was expelled while it was still a red giant. And the ultraviolet radiation ionizes that gas and causes it to glow. So what we see with the blue Snowball, I think you're a little overexposed here.
Yeah, I'm taking a new shot. It was 6400 was too much on the ISO.
So what we see with the blue Snowball and all these other planetary nebulae is a bubble of gas, or sometimes a kind of a hourglass shaped pattern of gas coming off of the white dwarf. Okay, a little bit better there.
Yeah, you could actually, if I zoom in here, you could actually see the internal structure there. And you could talk about that a little bit.
So what we've got the gas bubble around it, which glows in kind of a bluish green turquoise color. And that is caused by ionized oxygen being hit by the ultraviolet radiation. The gas that was thrown off by the star when it was a red giant is mostly hydrogen gas, but it does have oxygen in it. It's not the dominant gas. The hydrogen is the dominant gas. But oxygen, when it's ionized by ultraviolet radiation, it glows in a really bright turquoise color. And the hydrogen glows in a very dull red color. So the bright turquoise of the oxygen shows up much better than that dull red of the hydrogen. So this looks like it's a whole lot of oxygen, but it's actually just a small percentage of the total amount of gas that's surrounding the white dwarf. You can see the white dwarf right at the center of the bubble, and you see around it two arced bright regions, and that's actually a shock wave that is progressing outward from the star. Once that fusion process stopped at the core of whatever was left of the star, it collapses, and that collapse produces a secondary shock wave, which is now progressing outward through the gas. It's moving out away from the white dwarf faster than the gas that was expelled when it was a red giant. And so you can actually see that shock wave progressing outward from the white dwarf. And it's quite often that because of the planets or dust disk or whatever is around the star when it was still a full-size star. These things don't come off in uniform in all directions. They come off as a torus or some sort of elongated bubble from the center of the star. And so it's very common for us to see a shock wave progressing outward roughly from the equator, while we see the bubbles of gas coming off the poles. This one you don't see that very well, but quite a few other planetary nebula, you see it quite dramatically. There are planetary nebula out there that look like an hourglass out in space.
Steve asks, do white dwarfs eventually burn out? Yeah, they eventually will cool down. They'll stay hot for an extremely long time, in the billions, possibly trillions of years, but they will eventually cool down. Also, Germ says that we're providing or coming here is just the best way to see how silly our little planet's problems are.
That's why we keep coming here.
We're providing a calming effect, and that's good.
Yeah, calming effect on ourselves. That's why we spend so much time up here.
Yeah.
He's figured us out.
Yeah.
Gerald, I'm noticing, you were talking about the shock waves. I'm noticing on this picture of the blue snowball that out on the edge, it looks like there's a kind of a white band right here on the edge. And I'm wondering if that's like the remnant of some previous shock wave. Here's a recent bright one, and here's the remnant of an earlier one.
Yes,
that would make sense.
Yeah. When it was a red giant, it's not nice and stable. It actually pulsates because the nitrogen, or not nitrogen, helium fusion that's going on in the core turns on and off several times, and that causes the planet to, or the star rather, to pulsate, and that can produce miniature shock waves, if you will, in that bubble of gas that's surrounding it. So that's likely what you see there. Some of the images I've seen, like from Hubble Space Telescope and so on, you can see that there is not only down in that position there, which is about the 8 o'clock position, but there's another one up almost at the 1 o'clock position as well. So those are just, shock waves from earlier on in the process. Now, this object we think is about 1,800 light years away, and it's much smaller than some of the other nebula that we see that are farther away. So this tells us that this is actually fairly early in the process. So we're seeing this not long after the star collapsed and became a white dwarf. Over time, that bubble of gas is going to expand away from the white dwarf, and the blue snowball will get bigger, and it may change its appearance over time. So, if you want to hang around for a few 100,000 years, you might check that out.
Well, it's kind of cool to think that this the event that precipitated this was about the year 200, right? If it's 1,800 light years away.
Well, yeah, you're seeing it the way it looked in the year 200. Yeah.
But the event that started it goes back way farther than that.
Right.
A few tens of thousands of years.
And you're seeing a preview of what will happen to our sun in about 5 or 6 billion years. Stars like our sun die in this very slow process, resulting in a white dwarf surrounded by a planetary nebula. And it turns out more than 90% of all the stars die this way. A common misconception is that stars all die in a supernova explosion. It turns out it's fewer than or less than 10% of all the stars out there die in a supernova explosion. So you're seeing a preview of what's going to happen to our sun 5 or 6 billion years from now. Mark your calendars.
Yeah.
My calendar doesn't go up that high.
I don't think Outlook goes that far.
That's a future upgrade, right?
Yeah. Thanks for that correction, by the way. Of course, you're right. And 200 is when it looked like this if you were standing right next to it.
Yeah, one of the interesting things, a lot of people don't realize this, but when we're looking out into space, we are always looking backward in time. When we talk about some object that's, whether it's 10 light years away or 10 million light years away, we're talking not only the distance, but how far back in time. If we look at a galaxy that's, say, we were looking at one a while ago, it was 27 million light years away, right? That means that the light from that galaxy takes 27 million years to reach us. So what we see today is how the galaxy looked 27 million years ago. A light year is the distance that light travels in 1 year. So we use it as a distance measurement. So you hear astronomers talking all the time about, distances in light years, but it's also a measure of what we call look back time. We see objects out in space as they looked far back in time. So, your telescope is kind of like a little miniature time machine.
Well, I have a question for you, but there's also a related question here. Steve wanted to know how big is the green cloud itself? It's kind of hard to say that distance, but
a little less than 1 light year across.
Yeah, I was guessing anywhere from 1 to 5, and
the shock waves are moving outward at more than 100 kilometers per second, so they're really buzzing along.
So my question is, which is getting back to when I was sitting here speculating on what it looked like a couple thousand years ago and all that. How long does it take when a star finally reaches the point that it's forming a planetary nebula? How long does it take to reach this phase? From being a star to reaching this phase? Is there any estimates?
Well, let's take our sun as an example. So our sun was formed about 4.567 billion years ago. We actually know it that to that many decimal places. And it will continue as a main sequence star. So a star that is burning hydrogen at its core for probably another 4 billion years. It eventually will start burning helium, but once it starts that helium burning process, that's the beginning of the end for the star. Right. So from then until it becomes a white dwarf, at most, it's going to be maybe 1.5 billion years.
Did you say billion or million?
Billion. So from the time it starts burning helium to the time it becomes a white dwarf, it's a very relatively short time. So it spends about 10 billion years as a main sequence star. Then it goes through the process of fusing helium and then of fusing carbon and oxygen and so forth. But eventually, when that happens, it starts to swell up. It's the helium fusion that causes it to really start swelling up, and it becomes a red giant. And the process of actually shedding those outer layers for a star like our sun, probably 100,000 years.
Okay.
And then
that was my question. That was the essence of the question. So you get to the point where it's fusing the helium, it's becoming a red giant, it becomes gravitationally unstable, and it starts shedding the material and then creates the planetary nebula, leaving behind a white dwarf. That process of going from the red giant to the white dwarf while creating the planetary nebula is 100,000, 200,000 years, something like that.
In that ballpark.
Great. That answers my question.
Yeah. And then we believe, I think, that they'll be visible for another few tens of thousands of years beyond that before they expand out so far that they kind of disappear.
That gas is slowly spreading out, and eventually it will dissipate, and it will just kind of drift around the galaxy, eventually joining with other gases and dust and form new stars.
Little V wants to know if black dwarf stars exist.
Black
dwarf. I've heard of brown dwarf, but not black dwarf.
No, well, you could say that a black hole is a black dwarf.
I suppose.
Very much a dwarf.
Yes.
Yeah. Yeah. So no, there are no, things actually called a black dwarf. There are, as Richard said, black holes, but no black dwarfs that we know of. There are brown dwarfs, though. Brown dwarfs are very low mass stars that just barely have enough mass to generate heat and fusion. Uh, so they are so deep colored, so they put out so little light that they actually appear brown in color, and so those are called brown dwarfs. And they're very low mass stars, much smaller than our sun.
Oh, here comes a tough one.
Uh-oh.
What shape is the universe? Becky wants to know.
It's all around us. It's dimensionless. It's
a tough one to answer.
Yeah.
Yes, and we only are able to perceive a certain part of it because there is an information or light cone that we are able to see, and then whatever is beyond that is pure speculation. So it's bigger than what we can perceive, and it would be spherical in a sense, but that's also debatable. But you could say it's in pretty good shape overall.
Oh, Stephen's got a good one. How certain are astronomers about the timeline of our sun?
Pretty certain.
Pretty certain.
Yeah.
We've got a lot of different evidence that we use. So when I say 4.567, that is the official estimate of the age of the sun.
Any new photos of planets in our solar system? No, we don't have any tonight.
Yeah,
but we'll probably start collecting some for the winter months.
Yeah, unfortunately, Saturn, Jupiter, we can't view anymore. We do have photos taken with this telescope, but we haven't taken any recently with this telescope. We're not using the telescope nearly as much as we have in the past, because right now the Chabot Space and Science Center is officially closed for public activity, and we have very minimal activity up here with Chabot staff and volunteers. We are doing activities, but primarily what we're doing is virtual programming, like what you're watching now. And it's not going to be until for several months before we're going to be able to start bringing, full staff up here and opening the doors again for the public. So we are closed, just like so many other museums and commercial interests and so on, because of the pandemic.
Germ was forwarding a question from someone who had asked earlier. How do we measure the distance of galaxies from us? Well, it's always a series of calibrations to get all the way to the far galaxies. So for very distant galaxies, what we measure is something called redshift. And the farther away something is from us, the more its spectrum is shifted to the red because it's speeding away from us, and the light is getting stretched because of that acceleration away from our position as an observer. And the more it is redshifted, the farther away it is. And we know how to calibrate redshift such that we can convert that information to distance. And for closer objects, we don't necessarily use redshift. For closer objects, there are other methods that we can use, such as measuring the brightness of standard supernova explosions. There are particular types of supernova that are always intrinsically a certain brightness because the physics say X amount of energy will always be released from this type of supernova. And we can look at one of those supernovas and look at the characteristics and say, yeah, that's a standard candle, which is what it's called, and then see how bright or dim it is and know that based on that dimness, that it is X number of light years away. because the farther away it is, the dimmer it is. And there's, basic physics involved in the decrease in brightness as distance increases. So that's how we measure intermediate distances, and then close distances can be measured with parallax. As the Earth orbits the sun, we could take measurements of an object when it's on one side of the sun and then when it's on the other side of the sun, and see how it is shifted in the sky, and do trigonometry to figure out the distance. So all of these things build upon one another, starting with parallax and photometry, and moving to standard candles, and moving to redshift.
Yeah. So Richard, I promised a globular star cluster.
Oh yeah, let's go for it. Yeah, we're sitting here just gabbing, and we're ignoring what people really want to do is to see other stuff. So
yeah, you guys quit yakking and show us.
Show
us some cool stuff. So what I'd like to do is maybe go to a synchronizing star here.
Okay.
The one whose name we cannot say on public TV.
It starts with a
S. Yes. So we're going to go to that star.
Okay.
And we'll synchronize on it. So, one of the things that people are surprised to hear when we talk about the expansion of the universe and redshifting is, the faster.
Perfect. Perfect. You're really close here.
Yeah. So the farther away an object is in the universe, the faster it's moving away from us. Now, people intuitively can't fathom that. It's really hard to imagine why is it that it moves faster if it's farther away. And it has to do with the physics of a uniformly expanding
universe.
Yeah. And so what happens is, and there's a good way to demonstrate this. There's a really cool demonstration I do for kids at school with a long elastic band. And I, pin a bunch of stars to it, and I have them pick one and then measure the distances to all the others. And then we expand the band, and then we measure the distances again. And they discovered that whichever star they picked to be their star, if they then measure the distance to all the other stars, they are farther away. I'm still on that one star. So.
Oh, okay.
Well, stop gabbing and move the telescope.
Yeah, really.
Yeah. There we go. You're doing it again. No.
Yep. Okay, here we go. Slewing. So
stand by. That's another starburst for your momentary entertainment here. Ready? Okay.
Okay. All right. We're there now. Yep. So the next object we're going to look at is called a globular star cluster. This one is called M15. There are actually quite a few of them out there. Their globular star clusters are like balls of stars out in space. The ones around the Milky Way galaxy are mostly out in what we call the halo of the galaxy, rather than down in the spiral arms of the galaxy. And these are clusters of stars that all orbit around the center of the cluster. And then the cluster itself orbits around our galaxy. So you see here now, this is an image, and we're a little off center. So let me correct for that just a little bit. Okay, try it again if you want to. And this is several 100,000 stars clustered together. They are in orbit around the center of the cluster, but those orbits are highly elongated, very elliptical orbits. So the stars go in close to the center, swing around the center of the cluster, and then they swing far out to the fringe. When they're close in, they're moving very rapidly. When they're out at a great distance from the center, they are moving very slowly. And this cluster, you see a lot of stars are in very tight. So there are stars that swing way far out, and then there's others that are still in elliptical orbits, but they're very close in. And when we try to measure the mass of the cluster by measuring the velocity of the orbiting stars, we discover that there's a whole lot of mass very close to the center of this cluster. And that suggests to us that there may be an intermediate size black hole right at the center of the cluster. So this is called a core collapse globular star cluster because there's so many stars close into the center. And they are orbiting around, we think, a black hole that's right at the center. So people often mistake black holes and think, well, that black holes must suck them all in, but that's actually not the case. You can orbit around a black hole just fine as long as you're far enough away from it. And that's what these stars are doing. These globular clusters are very old. M15 is more than 10 billion years old. It's among the stars, or among the first stars to have formed when our galaxy formed. Now, most of the stars that formed when our galaxy were forming fell inward and became part of either the central bulge of the galaxy or in the spiral arms, but some of them clustered together out at the fringes of the galaxy and became these globular star clusters. There's some belief that some globular star clusters are actually remnants of other galaxies that merged with the Milky Way during its early formation process.
That's the theory I like because it kind of looks that way, but it's really debatable.
Yes. Yeah. Well, we do know that the stars are very old.
Yeah.
There are ways we have of measuring the ages of these clusters by looking at the types of stars that we see in the cluster. And all of the stars that we see are very, very old stars, like 10 billion years old or more. So that leads us to believe that these things have been around almost as long, if not as long, as the Milky Way.
And the way we know that they're old is we can look at their chemistry by putting a spectrograph as the instrument on the telescope, and we could see what type of elements are present in the star. And the old stars don't have any of the heavier elements that our star has.
Right. Yeah. And that tells us how old these stars are. Stars that form more recently, because they form from gas and dust left over from other stars, older stars, they have a lot more of the heavier elements in them. But stars that are very, very old have relatively little of the heavier elements. And that's one way we can tell how old they are. There's some other techniques as well, looking at the color temperature of the star and comparing it to what's called spectral broadening. When we look at the spectra of the stars, how wide are the spectral lines? That's another indication of the age of the star.
Nice.
All right.
Yep.
Okay. Well, it's 13 minutes after 10. Let's see if we've got any more questions that we need to answer. I do want to encourage everybody, if you're on Facebook, you'll see a donation button up at the top of the comment section. We can use all the help we can because the Chabot Space and Science Center is not open to the public right now. It means that one of our main sources of revenue is not happening. So we are relying a lot more now on donations. So if you've got a few bucks you want to give away, we would certainly appreciate it if you click on that donate button. You can also go to the Chabot Space and Science Center website, chabotspace.org. Chabot Space is all one word, .org. And when you go to the website, you'll see a donate button up at the top of the page, and just click on that. You can make a donation that way as well. And we would certainly appreciate it.
There was a question. It's related to what you were just talking about. Can stars orbit a black hole forever, or would they eventually get sucked in?
They can certainly orbit for a long time, and they don't necessarily get sucked in. They can also be ejected out as other material. They get entangled with other things. If two planets are orbiting, they get close enough together. If one is more massive than the other, its gravity can actually throw the smaller planet out away from the black hole. So
the famous slingshot effect.
Yeah. Now, black holes grow with time. When they do pull in mass, that increases the mass of the black hole. And that makes it larger. In fact, the size of the black hole increases in direct proportion to the increase in the mass of the black hole. And when we talk about a black hole, we have to differentiate between the object itself and the region around it. The black hole is not actually the object itself. The black hole is the region around what we call a singularity. And with a singularity, what's happened is all the mass that was once a star or many stars has now collapsed down and become so dense and so collapsed that it's literally a single point with the mass of all of those stars. And the more massive that singularity is, the bigger the region around the singularity, in which if you get that close to the singularity, any light that you generate cannot be seen by anybody outside of the black hole. So that's why they call it a black hole. You can't emit light from the interior of what we call the event horizon. So the black hole is just a region of space surrounding the singularity, and that region gets bigger the more mass that gets collected by the black hole or the singularity rather. All right.
Yep.
All right.
I just answered somebody's question on YouTube, and he was wondering if we could see the comet in Orion. There is a comet in Orion, and I saw a photograph of it the other night. But Orion is not really well positioned for us right now.
It's actually just coming into
barely
the point where we could see it, but it's time to.
Yeah, maybe next week we'll be able to do that. We'll have to plan for it and make sure we understand the position of that comet.
One of the problems we have here, we have 3 observatories, and there is a big observatory dome just to the southeast of the observatory we are in right now.
And where do you think Orion is?
Right, just on the other side of that dome.
Yeah. We create our own
just to the southeast.
So it's one of our frustrations here. Sometimes we get in our own way, So,
not much we can do about that.
Yeah. All right. Any other questions that we need to cover?
Can we see Uranus soon?
Well, actually, I think we can see it tonight.
Can we? We can do that.
Hang on just a second here.
Let's see, where is Uranus?
Uranus. Please. Sorry. Uranus. It's named after the father of the Titans in Greek mythology. Well.
What's our humidity at? Just to do a check.
Almost forgot about that.
Germ reminded us.
78%. We're good.
We're only a couple percentage more than you, Germ. So whatever that difference is between your house and the observatory is, that gap is closed.
Okay, so Uranus is nice and high. So away we go.
Okay, I'm going to have to 1600.
It's actually right by the meridian, about as high as it gets.
Yeah, not too far from the meridian.
Yeah, I wonder if we're going to have to. Yeah.
We might have to do a synchronizing star first.
We might. Want to give it a shot just in case?
Yeah, let's go ahead and shoot
Maybe
it.
we're lucky. Do you feel lucky?
Do you feel lucky?
Honk.
Yeah, probably half the audience out there has no idea what we're talking about.
Yeah, I know. We're old.
Too old.
Clint Eastwood, Dirty Harry.
Hey, you got it.
Hey, we got it. We got to move around a little bit here, but
let me reset this. There we go.
All right, maybe shoot it again.
Yeah, I'm going to shoot it again. I'm going to lower the ISO and try again.
So if we're lucky, we should be able to see a little bit of color. It will be more greenish than Neptune, yeah. Oh, we're down to 77%. Man, things are getting better by the minute here.
Yeah, and it's getting colder too.
Yeah.
Yep. There we go. Let me see if I could drop the brightness here. Yeah, I'm going to drop the exposure too.
You know, when you had the brighter exposure, I think I could see a couple of moons next to it. So
yeah, I still see those, but they're not as obvious. But let me first. I want to see if I can get the color right first. There we go, a little bit more. It's kind of a little bluish. It's kind of hard to tell. What do you think? Well, I agree we should go for the moons. It's more interesting that way. Go up to here. Try one more here. It's not being very cooperative with the color here.
There are 4 moons really in close that.
Yeah. Ariel, Oberon is actually looks like it might be up high a little bit.
Miranda.
And Ariel and Titania. Yep.
Okay, there we go. I see 3. I believe there's one really close.
Yeah,
right here. You're almost touching the sphere.
I think that's Ariel, and then the one to the right of the planet is Titania, and then the one high up above it is Oberon. Yeah. So you got a chance to see some moons.
Yeah. That's actually pretty neat. I don't think I've ever seen these moons before. Yeah.
So we started with a planet and we're ending with a planet.
That's pretty exciting. I didn't realize we could see that. Yeah.
All right.
Cool.
Okay. Well,
thanks everyone.
I think it's time we wind it up. We're down to 76%, so we got lucky tonight.
All right, and looks like we helped somebody get a 95% on their science astronomy exam. So mission accomplished.
Yeah.
Was that one of Alex
Congratulations.
Is that one of Alex Filippenko's students?
I don't know. I don't know if that's true, if it's Alex's students or not, but
I know they all
good news.
They all took their midterms on Monday, I think it was.
Where did you see it on YouTube?
Facebook. It was from a comment from Margot Ponce Diaz.
Oh.
So Margot, let us know. Are you a student at UC Berkeley or?
She's referring to Little V, so I'm not sure who Little V is.
All right. Anyway.
Oh well.
Congratulations. All right. Good night, everyone.
We'll take all the credit we can get.
Yeah, we'll take all the credit, whether or not we had anything to do with it.
Yeah. So, all right. Well, good night.
Good night, everybody.
We'll do this again next week, Saturday at 9 o'clock. So join us then. All right.
See you then. Bye-bye.